Here's some reaction data where we plotted concentration as a function of time. And so what could we do to figure out what the reaction order is? You know, once we figure that out, we pretty much solve the rate law, right? Yeah, we could graph it if a plot of, what would I plot to figure out whether it was first order? Yeah, if I plot the natural log of concentration versus time, and I get a straight line with a negative slope, that's the rate constant. Or maybe I could plot 1 over concentration versus time, and if I get a positive slope in a straight line. Well, nobody wants to watch me use Excel, and I'm not really good at making plots on the Texas Instrument. What other things might we look at to figure out what's going on here? What are hallmarks of first order? How about this? Natural log of a half never changes. Rate constant never changes. What does that tell me about half-life?
It's a constant.
It's a constant. So I start out with a concentration of 4.4 molar. What's half of 4.4? 2.2. And that took what? 1, 2, 3, 4 seconds. What would be 4 seconds later? That's down here at 8, right? What's curious about 1.1?
It's another half of 2.2.
Absolutely. And half of 1.1, that would be 12 seconds later. So what I'm seeing is a constant half-life. And so I can go, so we've answered part A. In fact, we'll just say first order. We solved the rate law too. A to products. Very generic. Well, we didn't solve everything, right? This is A. Let's go ahead and do part B. What is the value and units of K? Well, we'll use our handy-dandy equation. It says negative natural log of 1/2 divided by T 1/2, 4 seconds. That should give me everything I need. Negative natural log 0.5 divide 4 seconds. There's the value in units of the rate constant. Now that we know all that, we can go on and answer part C. What will be the concentration of A after 47 seconds have passed? Notice I can't read it off my data. Maybe we went that long. We don't know. We're not given that much information. But we established that we need to use this equation when we saw that we had a constant half-life. And we've solved for K right here. So we can probably just say, let's just solve for X times our 47 seconds and our initial concentration. Now I have that rate constant in my calculator of right now. I think I need that negative sign. I'm going to go times a -1. Alright, so now it's accounted for that negative sign. I'm going to go times 47 seconds plus natural log 4.4 in parentheses inner. So our property of logs say I can figure out X if I take E and raise it to that value there. So E raised to the negative 6.66287, which equals our concentration of A. It goes on for a while. That makes it consistent with our rest of our data. Any question? Now there could have been maybe some other approaches. I think pretty much the key is once we see a constant half-life, we know it's first order. Another approach might be to do something like this and plug in a couple of values and see if we get the same rate constant. So I'm going to just go 1.1, 4.4. That took 8 seconds. And see what kind of rate constant I get. Natural log 1.1 minus natural log 4.4. Okay, I'm going to hit enter at this point and then divide 8 seconds. And why don't I come down here to the bottom? There's my concentration at the very end of my plot. And this took 15 seconds. So I'll try the same idea here. Log 0.33 minus natural log 4.4. Then I want to hit enter before I divide. 15 seconds. There's a little bit of rounding difference. That's another way we could possibly check and make sure it's a first order reaction. Any questions on that problem? Consider the reaction X goes to products. The table below is the concentration of X measured in real time. 15 seconds does its thing. What is the reaction order? What is the value in units of K? How much time is required for the concentration of X to equal some other concentration that's beyond our table? So, do you think it is first order again? That'd be redundant to do two first order problems in a row, right? How do you know it's not first order? Yeah, the half-life isn't constant. Now, it's not quite as clean as the top here. Half of 4.4 is 2.2. Well, that's not quite, but it's close enough. Took 2 seconds. Half of 2.24 should be 1.21. 1.13 is close enough. And so if we kind of look at it, that's almost a half-life. That's almost a half-life. 1.13 divided by 2.56. So roughly, concentration is falling in half over these time intervals, and we see it's taking longer and longer. So if we don't want to plot, we have to look at these things. We could use this approach here, where we chose a couple intervals and the equation, the relevant equation, and saw if we got the same rate constant. We can do the same thing here. Only we want to use the second order equation. And that second order equation looks something like this. So if I solve for a rate constant and do it twice and get a constant, roughly the same number, I could convince myself that it is a second order equation because I'm using the second order equation. So let's just do this. And I'm going to say, alright, sometime down the road, what do we want to choose? How about 4 seconds? So how about 1.5 minus 4.4. That was 4 seconds down the road. That's going to equal K. So I subtracted 1 over initial concentration. That brought it across. Then I divided by time. And let's see what we get for K. 1 divide 1.5 minus 1 divide 4.4. I don't want to divide this last term by 4 seconds. I want to divide that difference by 4 seconds, so I must hit enter on my calculator and then divide 4 seconds. And there would be the rate constant if this is a second order reaction. Repeating 8484 everywhere. So let me do the same thing. Let's do 13 seconds. So I'm going to have 1 over 0.6, same initial concentration. That took 13 seconds. Let's see what that equals. 1 divide 0.6 minus 1 divide 4.4. Once again, I want to hit enter so that I divide 13 into that difference to 2 digits. That's looking pretty good. So we're going to assume second order. What is the reaction order? That means we know the rate law. Some constant. Now, me being an analytical chemist, I might say, well, some experimental error, not quite getting the same number. I think if I take the longest distance of time, I could get the most accurate reading. So I'm gonna just do that. I'm going to go 1 divided by 0.53 minus 1 divided by 4.4. That took 15 seconds. Let me see what my calculator gives me. 1 divide 0.53 minus 1 divide 4.4. Hit the enter key. Divide by 15 seconds. So these two values are a little closer, right? Now, me being the analytical chemist, I might want to take the average of all three. But you can see that these two are pretty close to each other. They're into 2 digits. They're all 0.11. So I'm pretty much convinced they're a constant. So how much time is required for the concentration of X to equal 0.25 molar? We're going to use the same equation, rearrange it in terms of time by subtracting 1 over X sub 0 from each side and then dividing by the rate constant. That's going to equal time. So here we go. 1 divided by 0.25 molar minus 1 over 4.4 molar divided by this rate constant. So here we go. 1 divide 0.25 minus 1 divide 4.4 divided by, I'm going to just scroll up and get that last one we did. Put it in there, hit enter. We're going to get 34 seconds. It's going to look like that. There's the units of the rate constant. Yeah, let me put that in. And then when you take this difference, you have an m and it cancels with that m and the second flips up top.
So does that mean the 2 m's in the numerator cancel each other? Or how does that go away?
That means you have, let me just do the top part. That means I have 3.77 molar divided by 0.11 moles per second.
Okay, that makes.
Yeah, so this difference equals that number. Like 3x minus 2x is 1x.